Okay, so here's just a problem we might see. We've got this fairly complicated looking molecule on the left. If you look closely at this, if you hit pause and study it a little bit, this is a polypeptide that's got some additional modifications to it. Okay, so we're going to take this short, so 1, 2, 3, we're going to take this tripeptide and we're going to heat it up in 3 molar sulfuric acid. So 3 molar sulfuric acid is going to be aqueous. So we've got a bunch of water, we've got strong acid. We're going to heat that at 110 degrees. And I didn't put this on here, but usually you do this overnight, 24 hours, something like that. So hit pause, figure out what all the products are, and come back, and I'll give you the answer. Pause. Okay. So these conditions are hydrolytic. And they're extreme. Okay, so you've got very strong acid, and you've got a very high temperature, and even though you don't see it, this is a fairly long duration hydrolysis. Okay, so the result of all this is, the extreme is hydrolyze every carboxylic acid derivative. Okay, so where are those? First, you got to find your carboxylic acid derivatives. There's one, that's an amide, so you've got a nitrogen bonded to a carbonyl. Here's another one, and this is what I say about it being a polypeptide, right? So that's alanine. If you hydrolyze this carboxyl to a carboxylic acid, you've got a methyl side chain, an amino group there. So these are all alpha amino acids. Here's another one. And then at the end, you've got an ester, so an oxygen bonded to a carbonyl, that's going to hydrolyze. And down here, the amino acid that's right here is cysteine, which would normally have an SH, but we've acylated it with paramethoxybenzoyl. And so we're going to hydrolyze that. All right, OCH3, nothing's going to happen there. OH, nothing's going to happen there. Okay, so now let's draw out the products for that. I'm going to see how far left I can go, how far right I can go, I guess. I can go quite a ways. Okay, so hydrolysis here is going to give us acetic acid. And again, everything's going to be protonated. All right, there I'm going to get alanine. So the carboxylic acid's protonated. Hydrolysis is going to give an amine. If I have alanine, neutral alanine, and I treat this with 3 molar sulfuric acid, I'm going to protonate that group. Right? Amines are fairly strong bases, so the amines in this reaction are going to be protonated. I'm just going to get a protonation event like that. The next one, I'm going to get cysteine. Again, keep that amine protonated. The cleavage here is going to give me paramethoxybenzoyl or benzoic acid. Okay. So when I cleave this bond, I'm going to get a carboxylic acid there. Remember, a hydrolysis is going to be water attacking the carbonyls. Kick electrons up, move some protons around, kick out the X group here. All right, I'm going to get serine. This is the amino acid with a CH2OH on it. All right, and then at the end, so I get serine by hydrolyzing that bond, that frees the amine. I hydrolyze that bond, which frees the carboxylic acid. And then I also get isobutanol. I think that's it, right? So we get acetic acid here, we get alanine, we get cysteine, Hydrolysis of the acylated thiol gives us paramethoxybenzoic acid. I get serine, and then I get isobutanol. So those are all the products. And so if you were doing this to analyze what the tripeptide was, you'd probably ignore the acetate, you'd ignore the isobutanol, the paramethoxybenzoyl, and you just look at the amino acids you had. We probably, given the circumstances, are not going to get to a lot of amino acid chemistry in this class, but you'll see it in biochemistry if you take that.